Hello. Oh, I missed all the good stuff. I'm trying to talk into the microphone low and close like we used to when I did college radio. But, there we go. Sorry about that. Getting things set up, I was making sure the slides were there. That's why there was a little bit of a delay on me talking. To point out, Bill found an error in one of the Pearson problems. I'm going through with Pearson to see why that happened. I'm actually leaving it up there to see if the rest of you can spot it. I'm actually trying to get it fixed, and it doesn't look like it happens in every random version of the numbers. It looks like it happens in a certain variety. The actual similar thing happened in my functions and modeling class, where one of the roots for a polynomial was incorrect, but it was only on certain randomizations of it. What Pearson does is they kind of put together a formula that will work for any set of numbers in them, but I think sometimes when it picks a random value, there can be rounding errors on it, and I've been choosing from test bank questions, which might not have the best rounding algorithms in them. So I'm looking at it. Thank Bill for picking that out, and like I said, it doesn't seem to be happening to everyone, but I've been trying to remove questions that do that. Let's see, everything is up on Pearson, all the due dates are there. We're winding our way through. We'll finish chapter 7 this week and do the 2 bits in chapter 9 at the end. It's kind of how last semester went. It's always weird, end of semesters, the conversations kind of flow a little more quickly because you've been doing all the background work to get the conversation going. And there's always like the drum beat at the end of the semester coming through. This one feels slightly odd. I don't know why. It might be I'm standing on a porch staring at a rainy Vermont when I should be staring at people kind of half asleep in a classroom. But that said, hypothesis testing and regression are kind of the nice tools that come out of it. You have done all the work to make this stuff happen. But if you look at the sections here, we're doing hypothesis testing with the for the mean with the standard population standard deviation known. We'll do it with the population standard deviation unknown, and that looks like what we did with the confidence intervals using Z tables or T tables. All that we change up on it is we kind of have to find these p-values hiding in the background. So it can be a little quick as I go through the tests here. Holler if you need me to look back at something, and I'll try to put a couple examples up as we go through the examples on it. As with any of these tests, I strongly recommend drawing or sketching your normal curve or your t-curve and figuring out where your endpoints are, especially as we get multiple tails here. So that being said, let me see if I can open this up and get it started without losing you. Yep, you're still on the side. We're looking okay here. So what we want to do is we want to interpret what p-values are, which are the values that we need to compare if we're going to reject the null hypothesis or fail to reject the null hypothesis. We want to find critical values, which are the Z critical or T critical. In this case, it's going to be Z critical, which give us the boundaries. And so the big question really ends up being where our tails are. And we'll use rejection regions. These are new words onto the same figures. So if our p-value is less than or equal to the alpha value, which we set how sure we want to be in our hypothesis testing. We set our percentage of that. So alpha is something we set. If we're less than or equal to that, we reject the null hypothesis. And we say that there is not enough evidence to support the null hypothesis. And if the p-value is greater than alpha, then we fail to reject the null hypothesis. Now, depending on which we made our claim, we then word appropriately from it, because our claim can be the null hypothesis or it can be the alternative hypothesis. And so our decision rule really comes on calculating this p-value and comparing it to the I want to give a good word for alpha. It's the certainty that we want our tests to be made. It's the I'm trying to think of a good. I'm flipping through the book to see, going back into the previous setting, the level of significance. It is a percentage, so I have always kind of termed it in like level of certainty, level of significance, or percent certainty. Significance won't work. So the p-value for a hypothesis test is 0.0237, and if our level of significance was 5%, we notice that this p-value is less than 5%. And so being less than 5%, we would reject the null hypothesis. But if we wanted a higher level of significance, a smaller percentage, right? The smaller the percent, the more significant our result is, the better it is. If we want to less error, right? If we think it as the percent of error that we're willing to accept, and an alpha of 5 is like 5%, and an alpha of 0.01 is 1%. If we increase our decrease our level of error, increase our level of certainty, and you get 0.0237 is greater than 0.01, then we fail to reject the null hypothesis. And what we want to think about here is what we're doing is we're saying we only want 5. It's not like 5% error. It is a strange word. We want our error, how often that we generate type 2 errors, to be 5% of the possibilities of our error space for an alpha equals 0.05. For it to be 0.01, we want less error in our decision. Now, just like in confidence intervals, the more certainty we put into things, the wider our spread gets, which means that it's harder and harder for us to match p-values into this. We have a smaller and smaller region we need to match. The more certain we are, the harder it is to guarantee things. And that's the nature of statistics. It's the nature of quantifying uncertainty. The more certainty you want, it's harder and harder to match those the areas that you're trying. And so for these hypotheses that we're claiming, if we want to come up with a new piece of knowledge with a very small alpha value, our p-values are going to have to be very small. And you'll see where our p-values come from here. So if we're going to find a p-value for a hypothesis test, we have to look at what type of test we have. And so we were using the symbol on the alternative test, or the alternative hypothesis. Remember, the symbol on the alternative test, if it's pointing to the left, was a left-tailed, right? That's a less than sign. If the alternative hypothesis was pointing to the right, it's right-tailed. And if it was a not equal sign for the alternative test, we had a two-tailed test. And so the p-value is the area shaded in that direction. And so only one word done over here, so I'm going through. Looking at this, the p-value for a left-tailed hypothesis test with a test statistic of z equals negative 2.23. And you want to decide whether the level of significance is alpha equals 1%. And so a left-tailed test, you're looking at the probability of the shaded in blue area. So you have a z value of negative 2.23. So you do what we've always done with z values. You go to the table. Let me pull the table up here. have it right here. I'm going to lose sight of you guys for a second as I do this. But here's our tables again. That we tend to use these. And so any Z value we need to look up for a standard normal distribution. So we find the negative 2.23, I believe it was. And 0.0129 or 1.29%. 0.1029? Yeah. All right. And so notice that process hasn't changed. These areas under these curves give us the same values from the same tables. What we're using is what that probability space means, because now we're looking at the probability of how much error we're getting in versus type 2 and type 1 errors. All right. So we're not talking about the distribution itself. We're talking about the chance of error when we make a decision. And again, I'll have to repeat because we keep doing the same mathematical thing. I asked my graduate advisor why everything ended up being e to the something, which is the function that makes the normal curve is a Gaussian, and it's e to the x squared minus, or x minus mu quantity squared divided by standard deviation squared. To e to something. Everything was e to something. And she just said it's the tool we have that works. And what you find is that the probability of being right and wrong, the probability of being near the truth or away from the truth, all of these different things that we fall back into the probability rules for, we're falling into, we have truly randomized something. And so we're going to differentiate from whatever we're looking at using this exponential function. And so now that we're looking at our chance of being right or wrong, or where our type 1 and type 2 errors fall into play, it falls into the same normalized distribution. It falls into the same curve. We're not looking at the same normal. We're not looking at the same type of data. We're looking at that data as it relates to the error, and the type 1 and type 2 error. And so we keep going back to the same tables, and we keep creating these new critical values that we're looking for, but we're applying them to different circumstances. And those circumstances in this case happens to be how our error goes. All right, and I'm going to skip the Excel on this. So now if you want to find the area of a two-tailed hypothesis test, the thing that you have to do is realize that on a two-tailed, let's see if I can draw on here without causing huge problems. That on a two-tail with a Z of 2.14, half of your p-value is here, and half of your p-value is here. And so you have to take the error of one of the tail parts and multiply it by 2. And that's what the 2 is showing here, that you're going to multiply this by 2. Now your Z score takes you up to here. And so what you want to do, oops, let me get rid of my ink on here. I like my blackboard, but I do have to find a way of drawing on the slides better. The built-in pen that they have is not the best. Find a way of like putting the opacity down on my blackboard. I'll overlay it over top, but I'll behave. So if we have a particular critical value score and it's a two-tailed test, we need to find is the area up to 2.14. That's what the table is going to show us, and it shows us the 0.9838%. But that's the area up to that. So we take the complement of that, and we get the 0.0162. And so that is the area of the shaded region on the right side. Remember, all of our table values are left-tailed. So if we do anything right-tailed, we need to do 1 minus what we looked up in the table. If we do a two-tailed, and we're looking at the far right value, we do the 1 minus, but then we multiply the result by 2. We take however much is in this shaded area, and we multiply it by 2 to get the amount in the other shaded side. The nice thing about our normal curve is it's symmetrical. It's symmetrical across the mean. So whatever you get on one side, you get the exact same amount on the other for two-tailed curves. So that's where the number 2 comes into play here for the two-tailed curve. And multiply. All right, so let's look at one of these here. I'm going to flip into the back of the book here. 2 seconds as I pull over to this. All right, on the blackboard here. So if we have a Z critical value that we look up from our statistics, and I'll show you how to draw the hypothesis in. Right now, we're looking up p-values based off of the critical scores, and then we'll put this into an actual decision-making process. Right? So if we have a Z critical value of 1.64, and it is a, what type of test? It's a two-tailed test. So our alternative hypothesis, right, was some mean value not equal to whatever we're testing against, right? Or test mean. So I think what did the book use as its variable? The book used K's, right? All right, so this is it. We're having a two-tailed test, and the critical value we looked up ends up being 1.64. Now, our level of confidence, we set alpha as being 0.10, or we want 10% is what we're looking at as our significance level. So what we need to find is, and here's what I say, always draw out your normal curve. And we're going to look up what a Z of 1.64 is. But this is a two-tailed distribution. Because this was a not equal in the alternative, it makes it two-tailed. So we're going to try to end up finding what the area is on these two parts. Well, what's nice is this is a normal. So when I look up on my table, I'm going to get the area of all of this. So whatever I get out of my table, I have to subtract 1 from it. So let's do that. Let's go over to our table here. There's browser. And that's you guys. Say hi to yourselves. There we go. So I have 1.64. So that's a T table. I want a 1.64. So there's 1.6. 1.64 is 0.9495. 0.9495. Here. So that is 0.9495. But that's not the area here. So that area is 1 minus 0.9495, which is equal to what? 0.0505, I think. I'll grab my calculator here. Write things down on a piece of paper, but you should always double check them. Yep, 0.0505. And so the area inside one of these tails is 0.0505. But my p-value is the area of two tails. So p is going to be 2 times 0.0505. I have developed I don't like two-tailed tests because I have to remember to multiply by 2. And I get that as my answer. Well, this p-value is greater than alpha. And it's greater than alpha by 1,000. which means we fail to reject the null hypothesis. Fail to reject the null. And so that's what we mean by a test. We have some critical value we look up based off of our test. Well, let's make a test from beginning to end here and put each piece of it together. So we'll use, oh yeah, I like this one. There's the pit crew problem that's on the slides. I'm trying to get the pit crew problem out. And we'll move it here. Let me get the pit crew. All right. Let me. Flip that over. You should be seeing the slides now. So the idea here is that we're going to use a z-score test to test for the mean. And we're going to test the population mean using our sample statistics. So we generate our z-score. Now here are the conditions we need met. And these are the conditions that have not changed for us. The sample is random. I've been shouting that louder and louder every day coming through. If you mess up randomization, you skew your data. And the population is normally distributed, or you have more than 30 samples. And the standard error, the mean, is the population standard deviation divided by the square root of n. So remember when we were doing the averages of the averages, we got this special standard error of the mean symbol. Well, that in itself is the population divided by square root n. And this was the thing that we looked at, that the more n you have, the narrower your distribution could be, but it goes up slow. And so we're going to want to state our null hypothesis and our alternative hypothesis. We're going to want to specify our level of significance, which this is the stuff we worked on the last time. And then we want to find the z-score and find the p-value, depending on the type of test we have. And the p-value and the type of test is going to determine on what part of the tail we look at and how we look at the tails. So let's put one of these together. I want to see, and then we make our decision. Yeah, this is the one I want. So in auto racing, a pit stop is where a racing vehicle stops for new tires, fuel repairs, and other mechanical adjustments. The efficiency of a pit crew that makes these adjustments can affect the outcome of a race. A pit crew claims that its mean pit stop time for 4 new tires and fuel is less than 13 seconds. A random sample of 32 pit stop times has a sample mean of 12.9 seconds. Assume the population standard deviation is 0.19 seconds. Is there enough evidence to support this claim with a 1% level of significance or 0.01 significance? So I'm going to go through this, and we're going to do this. So first off, I'm going to look here. First thing I find is my n is greater than 30. And it was random. Now, the claim is that the time is less than 13. So we have some value less than 13. There's no equal to it, so this would be my alternative hypothesis. My null hypothesis would be that value is greater than or equal to 13. And what are we using? We're testing for mu, so I'll replace these now with mu greater than 13 or mu less than 13. And I want to make sure that's my claim. All right, so that's the claim they're making. We now want to find out if there is enough evidence to support the claim. So we're going to have to test our null hypothesis. So I have enough here. I'm going to switch over to the blackboard and we'll work this out mathematically. But this is the idea of how we take a claim and test it. They're saying, hey, we're better than 13 seconds. We do some random tests. Now we're going to test that claim to a percentage of accuracy. And that percentage of accuracy you can use to calculate further. I don't know if you ever heard Moneyball and a lot of the sabermetrics and the different types of sports analysis. This is part of the thing they do is you randomly sample the data coming from athletes and you look at how significant their ability to hit their averages. If they hit an average of one thing, but it's very, very largely spread, it's not that significant. And that's what's happening here. You have a pit crew, you've got enough random samples, you want to test that. And the more data we gather, the more we can use these to make predictive things. But let's put this together here. Let me scroll down here. All right, so my null hypothesis was that my mean was greater than or equal to 13. My alternative hypothesis was that the mean was less than 13, and that was the claim. All right, so I'm labeling those things. So my level of significance was 1%. I only want a 1% level of error on this. So how can we test this claim? All right. Well, I'm looking through here. The sample has a mean of 12.9. Assume that the population standard deviation is 0.19 seconds. So I have enough data from all pit stops that I can tell what the population is. Now, I want to think of this in perspective because we talk about populations and samples a lot. Let's say I am collecting all race data. I would have every single time that they have changed the tires. I would have all of that. I would be able to calculate this. Now, the reason I'm only testing a random sample out of what they could do could be related to what the population data is. So I have the past and I have the present. And so I have the whole population here, and I am randomly taking from here to see if my data is progressing into the future in a way that I like. And that's valid. We can look at a smaller chunk of events, especially if the number of things they have are very large. We can have the total statistic, but we can look at things nearby. It's random-ish, and it's good for predicting what we might want to be of a population. We're random within this section, right? And I'm doing time as progressing from the past towards the future. Because remember, what we want to do is we want to predict future events. That's what we do mathematics for, and we want to predict them with levels of certainty or significance. So we can make this assumption if we have enough data from enough experience. We will find in the next section we can do this if we don't know what the population is doing. So we need to make a z-score. We need to take our averages and subtract them through the mean that we think they're going to get, and then from the standard error. And so our averages was 12.9 seconds, and the claim average is 13. The population standard deviation, let's see, is 0. This is the population divided by square root of n. So I'll put this all down here like your book does. Not a big fan of that, but 0.19 divided by square root of 32. I can put that all in the calculator if I remember to put parentheses around these two things. And I'll do that right now. And we'll get our z-score. But notice what I've done. We have a claim that's being made by this pit crew. And we're testing that claim to a level of significance. We're basically seeing how much type 2 errors we can take if this claim is being made. So let's see, I have 12.9 minus 13 quantity divided by 0.19 divided by square root of 32. Second square root 32. Whoops. I am not a fan of these calculators that try to intelligently put things into parentheses for you. What did I miss there? I got a letter K in there somehow. Alright, let's get that letter K out of there. Quick. Typos. Wish I had my camera. Don't have it yet. That has been a function and a half. There we go. I get a negative 2.977291710. And since our table only goes to 2 decimal places, I'll round that like that. So I have a z-score, or a critical z-score. Now notice my alternative is looking for a left-tailed test. So there's my Z critical, and there is my left tail. And it's nice that our alternative is looking for a left tail. So let's go to our table and look up what negative 2.98 is. There you guys are again. Say hi to yourselves. Okay, so I'm on the negative part of the table, which is here. And 2.98, I'm getting 0.0014. So my p-value is 0.0014. So my p-value is less than alpha. Hoping it's less than alpha. Let's see. My p-value is 0.0014, which is less than 0.01. Yeah, that's true. Those ones in there got me. So being less than, we reject the null hypothesis. Right? And on your book on page 363 is our decision base. If p is less than or equal to alpha, we reject the null hypothesis. So we reject the whole null hypothesis. So we reject this. This is rejected. That means we can say there is enough evidence to support the claim with 1% significance. So by rejecting the null hypothesis, it means our claim has enough evidence to support it. And so there is enough evidence that we can say this pit crew has less than a 13-second pit time. And that's how our testing pulls together. And so that's how hypothesis testing works its way through. All right, let's look at another one here. Yeah, this will be a two-tailed one. And I think we'll then look at rejection regions a little bit. We'll do this one. Let's see. Yeah, I'll use example 5 in the textbook. I was going to look at doing example 6, but we'll do it at example 5. One of the things I tend to do when looking at these is read these and kind of get an idea of where we're at and what we need from this. So, according to a study, U.S. homes that use heating equipment the mean indoor temperature at night during winter is 68.3 degrees Fahrenheit. You think this information is incorrect. You randomly select 25 U.S. homes that use heating equipment in the winter and find that the mean indoor temperature is 67.2. From past studies, the population standard deviation is known to be 3.5 degrees Fahrenheit, all garbled there, sorry about this. And the population is normally distributed. Is there enough evidence to support your claim at a level of significance of 5%? And so we want to use a p-value. So the first thing here is you don't have more than 30 samples. You have 25. So we need enough information about this to say that it's normally distributed. Having a standard deviation from previous surveys would be enough to say this. I would, as a scientist, because there is a mechanism that drives temperature changes and people's reaction to it, I would have this be regionally dependent before I could say it was normal. Because I think if you did a spread of the United States, you would find that between humidity levels and latitude, there would be different temperatures that people find acceptable, right? When it's more humid, you can have a lower temperature feel warmer because the moisture in the air holds heat in better, right? In the winter up here in Vermont, I try to make sure I have a humidifier going so that, actually, for me, it's a lot of times just putting water on top of the wood fire, right? But that moisture in the air helps holding heat. So there would be some things about this that, depending on the region of this survey, I would question the randomization of it. It was normal. But if we were just looking at like within a state or within a county, this is acceptable to be normal. Now, I know this is more than what a textbook question is asking, but I want you to think of these things when you see how these decision processes are going. When you're thinking truly random and you know that there might be mechanisms in the background of the data, you have to acknowledge that. And so for this, in the parameters of this question, it makes sense. But if it was something I was doing in a larger area, if I was truly doing all of the U.S. and I had access to a large quantity of the homes, I would try to make sure that I broke it down into region to take environmental factors in, right? These things are only as good as what we understand about them. But let's use the question for what it's worth, and let's come back here. So what we want to do is, this is the sample mean. No, this is the sample mean, so this is X bar. And this is what we're testing against mu. According to today, so you think this information is incorrect. So our claim is that it is not equal to 68.3. And we're doing an equal sign. So let's come over here. We have our information. Let's put this together here. So we're saying that the mu is not equal to the 68.3 degrees Fahrenheit. Notice I immediately put that into the alternative hypothesis because the null hypothesis gets the symbol of equality. And so I knew my claim was going to be an alternative because it was not equal. So the null hypothesis is it's equal to 68.3. So, and we want to do it to a level of significance of 5%. So 0.05. So that's our test. We measured 67.2 degrees Fahrenheit. Our population standard deviation was 3.5 from previous surveys. And we tested 25 homes. So that's the information we need to make this test work. We have our claim. Let me put our claim here, because we're going to talk about our claim in a bit. So this is an inequality. Inequalities, we use the symbol here. And so our p-value is going to be a two-tailed test. It's going to be the stuff within here. All right, so we have a normally distributed curve. We're going to need to find our z value, which is x bar minus mu over the standard deviation of the mean, or the standard error. And so the standard deviation of the mean is the population standard deviation over square root n. So again, I can fill everything in that we have. So we have the 67.2 degrees Fahrenheit minus 68.3 degrees Fahrenheit all over, let's see here, 3.5 divided by the square root of 25. All right. Let's see if I can type this all in my calculator without making a typo. And we get a z value of -1 point. Again, 2 decimal places is all we need because that's what our tables have. Well, if I look this up in my table, I get that my table value for this has a probability of 0. And it's going to be this tail here. So I'm just going to call this tail 1. We'll call it T1. Give it a label. So let's see. Tail 1, T1. If I look it up in the table, I get 0. Is this showing right? Let's see. Yeah, it is showing right. 0.0582. But being a two-tailed test, because this was an inequality of an equal sign, not a less than or greater than, I need to multiply this by 2. 4, 6, carry my 1, 1, 1. So my p-value is 0.1164. Now I have to compare my p-value to my alpha. And so my alpha value, my level of significance, was 0.05. 0.05, 0.05. Well, this is definitely greater than 0.05. So we fail to reject the null hypothesis. And so we say that there is not enough evidence at 5% for the claim, right? Because our claim was the alternative hypothesis. We've failed to reject the null, so there's not enough evidence for our claim. And so we can't say that the 68.3 is wrong. There's just not enough evidence for it. The other thing we can do, instead of doing just straight out tests, is we can look at things called rejection regions. And we kind of turn the Z critical scores into values that relate to the mean that we're looking at. And so we find a way to turn them into critical value regions. And they fall naturally. There's a nice table for them of particular critical values that come out. And they make some of the tests a little bit easier to look at. So let me get over to the slides here, and we'll just go through this table of values. If that's switched over for you, good. All right. So this. was the one we just looked at. All right. So these are the range of values for which the null hypothesis is not provable. Rejection regions or a critical region. And we can kind of define these, especially for set values of alpha. We can make a range of values that we can set. And so if your test fails to fall within this region, then the null hypothesis is rejected. Or, if this test falls in the region, then the null hypothesis is rejected. It's a rejection region. And so the critical values separate the rejection region from the non-rejection region. So, I hate these animations. Let's go back. Here. So you always start by finding the level of significance you want and the type of test you have. Is it a left, right, or two-tailed? Remember, again, the type of test comes from your alternative hypothesis, right? So an alternative hypothesis that has a less than sign is left-tailed because it points left. An alternative hypothesis that has a greater than sign is right-tailed because it points right. And an alternative hypothesis that's not equaled is two-tailed. The mathematical symbol you use for the alternative hypothesis tells you the type of tail to take. And now you want to, so once you determine if it's left or right-tailed, then you need to find the area that corresponds to alpha. And so when we drew our bits here, and I was going, okay, if it's a left-tailed, this region here, we look up this number, and that'll give us our p-value. Well, this actually ends up being our alpha that we're looking at. And so we can find the boundary of the alpha value. And if it's right-tailed, right, we can find the boundary of 1 minus alpha. And that's what these values come into. Now on the two-tailed, you find this alpha, and remember the alpha is over both of these. So when we were finding the p-value, we multiplied it by 2. Well, here we take half. And so what it's saying is, look up your alpha, and you can find a z-score that reflects that. And so let's put these in. There's a nice table. And so you sketch your test and your alpha values, which I just did on the other slide there, forgetting that they're going to show them to me. And you'll get your critical value, your region. If you fall into this region here, that's your rejection. Oops, go forward. There we go. And so you find the critical value and you look at it. So here they're going an alpha of 0.01. Now there is a chart. And let me get you back over to charts here. Say hello to yourselves again, because I see you all there. Let's come over here. Where did it go? It is just in the book, not on the set of tables. Let's see here. Get back here. Get back to here. Alright. Bring you guys back. Hello again. Are we off of that? There we go. Alright. So, on page 369 of the book, it lists the commonly used alpha values. And to be honest, I was just doing something for the Department of Higher Education, and they were using an alpha value of 0.05. You will tend to see that people only use these alpha values of 0.01, 0.05, 0.10. And they give you the following critical values. So if I have an alpha or a 10% level of significance, and I'm left-tailed, then my critical Z value is negative 1.28. Now this would be the same as looking up 10% in the chart and walking it back to the Z value. If I'm right-tailed, it's positive 1.28. And if I'm two-tailed, I have a positive side and a negative side, right? And so that's a plus minus of 1.645. If I have an alpha value of 5% and I'm left-tailed, my critical value is negative 1.645. And notice that kind of makes sense because remember how the two-tailed was half? Well, this is now half. And so it gets the same. If I'm right, a 1.645. And if I'm 2, I'd be looking up what would be 0.025. So that's plus or minus 1.96. And at 1%, if I'm left-tailed, I'm negative 2.33 is my Z critical score. If I'm right-tailed, I'm 2.33. And if I'm two-tailed, I'm plus or minus 2.575. And most people, when doing hypothesis testing, pick known alpha values so that these critical regions are easy to look up. They don't have to recalculate them. In fact, a lot of times in physics, they'll use a 6 sigma, or a 5 sigma, sorry. 5 standard deviations, because that relates directly to a Z critical of plus or minus 5 on either side. And so you can experimentally, you can pick your Z boundary score, or you can pick the percent level of confidence, and there are common scores for it. I would say that table on 369 saves you from looking it up. I'm surprised it's not on that front matter sheet, and it might actually be a page or two deeper in there. And of course, this did not switch over to the blackboard. Here's the chart I wanted to write for you, the page 169. The left is negative 1.28, the right is 1.28. My apologies. For some reason, this periodically bounces down one window on me here, and I'm not always getting the blackboard shown through as it bounces down one window. Okay, and so these developed a region. Let's look at one test of a rejection region. I'll use an example. I think the example puts it all together. Yeah, let's go through here. I want to pick this last example because this is how I want to finish the known means. So let's see. Oh, the methodology is almost exactly the same as what we did when we were comparing a p-value, but what we're doing is instead of having a p-value, we have the rejection region to compare our actual data to. So we'll look at this. Research, yeah. Let's get you over to the slides here. So watch and compare to what we did. We're not going to calculate the p-value. We're going to use the rejection region to do that work for us. Most of the steps end up being exactly the same, except the value we the value we compare against. Okay. So a researcher claims that the mean annual cost of raising a child by married couples in the U.S. is $14,050. In a random sample of married coupled families in the U.S., the mean annual cost of raising a child is $13,795. The sample consists of 500 children. Assume the population standard deviation is $2,875. At a significance level of 10%, is there enough evidence to reject the claim? So we still have to do the same work here. We still have to figure out what our alternative is, and then we'll look at our rejection region. So let's take all of this information. So the claim is that the mean annual cost of raising a child is $14,000. So the claim is mu equals 14050. So that's going to be the null hypothesis because it's an inequality. So the alternative is 140504. We have our sample average, and we have our number of samples, and we have our significance level. So let's turn this significance level into critical values that we can compare against. So I'm going to try to switch back to the blackboard, see if it works. There it is. If that pops back, let me know. All right, so our claim was our null hypothesis, which the mean, that should be null hypothesis, $14,050. So our alternative hypothesis is not equal to that. Yep, I put my not equal in. We want an alpha of 0.01 or 0.1, sorry. 10%, yep. And we had an N of 500. There are 500 children in it. And a population standard deviation of $2,875. All right, we have the data we need to go. So this is going to be a two-tailed test. It is a two-tailed test at 10% level of significance. So I'm going to come back up to the table I made here. 10% significance, two-tailed. My critical values are going to be this. Right? 1.645. So I'll pull that down here. And so my Z critical is plus or minus 1.645. Those are the critical values that defines my rejection region and what I can or can't do. So if I fall within a rejection region, I'm going to reject the null hypothesis. If it falls out of the rejection region, I fail to reject the null hypothesis. Right? And these are my rejection regions, with that being 1.645 negative, 1.645, and 1.645 positive. Right? So if my Z values fall in here or here, I'm going to reject the null hypothesis. If my Z value falls within here, I fail to reject the null hypothesis. So these set values or these set levels of alpha means that to do my test, I calculate my z-score, which is going to be what I got from my sample. My sample average. Please. Let's look on the slide really quick. 13,795, right? 13,795. So we'll come back here. My sample. It's 13,795. So 13,795 minus 14050 over 2875 divided by the square root of 500. Right? The sample average minus the mu, right? X bar minus mu over sigma divided by square root of n. And a calculator away, I get this is negative 1.98. Well, negative 1.98 is in there somewhere. And so we reject the null hypothesis. Well, let's go back and look at our null hypothesis. Our null hypothesis was our claim. And so we can say there is not enough evidence to support the claim, or there is enough evidence to reject the claim with a 10% level of significance. And so the researchers' claim we reject. Because the evidence at 10% level of significance let us reject that. All right, so that finishes section 7.2. Seven 7.3 is exactly the same. Except we don't know the population standard deviation, so we use t-tables. All right, my recommendation, practice the homework. Ask me questions on the homework, and I will start talking about 7.3 and 7.4 on Wednesday. I'm starting to get my days of the week right as we work our way to the end here. We'll do the proportion testing. I'm going to go really quick through the t-table stuff. Give it a read through, practice the homework, shout. Yes, Bill, but not professionally. So Bill asked, am I doing any analysis on the virus? Back at the end of January, early February, someone had asked me to look at this from a logistical exponential curve on what the doubling rates would be like, and they were just curious about how long it would be until it was I basically calculated how long it would take if nothing was done. And this was before China put its lockdown through. I think the doubling rate was at 4 days at that point in time. And it calculated by June, everyone in the world would have it, which had implications for like hospital use. As soon as China locked down and people went into social distancing, the doubling rate has spread out, and that spread out of doubling rate has eased resources. But that's the only analysis I've done, and I haven't done any statistical analysis on it. To be honest, the mathematics behind it aren't, I don't want to say are complex. What always happens with any statistical analysis is knowing your parameters. We're talking about how we can survey and measure things here and how important those values are for it. There's a technique called Bayesian statistics where you can take what is known and update it as soon as information changes. It takes into account that you don't know everything, and this type of statistical analysis would go into Bayesian things because our observations are limited to what we can see. There's a whole bunch of unknowns coming through, but they can be accounted for. So a lot of the models you're seeing have these wide varieties based off of the uncertainty and the unknown parameters that we know are out there. And so any model like this, every variable has to be accounted for. And the type of variables we're looking for here are large. I've been reading some of them, but I haven't been doing any other than those early exponential calculations I did for a friend that had some questions on it. And to be honest, I'm actually surprised that we did slow down the doubling rate, as far as we know. But anyway, to answer your question, Bill, it's funny. There's been a couple questions in homework for both my functions class and in here that I've actually skipped because they have dealt with respiratory illness percentages and viral infection rates calculating wise, because I didn't want really to hit anyone's stress or anxiety on it. These are things that we can look at a low level value, not a low level, at without extremely deep analysis that can give a good macro picture of what's going on. If you're interested, Bill, I can send you some of those questions if I can find them here, of what we can look at. I know it's not within the hypothesis testing, but I think it was a couple chapters back where we looked at some different health statistics that I skipped over the questions that Pearson was asking. You guys have a wonderful time, all right? And yeah, you're right, Bill. This can be a little confusing because we're testing a claim, and we're not used to mathematically finding a way to test things, right? You're either right or wrong, and here you're going, I have 10% I'm right, or there's a chance if I allow for 10% error, this claim is good. If I allow for 5% error, this claim is good. If I allow for 1% error, the claim is good. And that is a confusing thing, but I do think it's a useful tool. All right, everyone have a wonderful, 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 wonderful time. If you need anything, please email me. All right? Hope to see you guys soon.